thought if I just did the first step of this orthogonalization process, then it might mislead you into thinking that there's not a lot of math to be done in computing these things, but it turns out there is. But this will be our third orthogonal vector, and what we would have here is an orthogonal set, and if we felt so inclined, we could divide each of these by the norms and have an orthonormal set. Okay. Now you could see from what I did here that there was nothing in this process that I couldn't do with just any arbitrary vectors. Right? Any arbitrary vectors in some Rn. And so that is the case, of course. That is true. Yes?
What if I'm confused? So if I say something wrong, it's very likely. But so on the web work from the other day, it was like when you project something, you project it onto a line. And so there's one vector, and then you're finding I think you're finding y hat, which is orthogonal, right, to y. And that's the case for, since it's a line, is that the space defined with a basis of only one vector, and that's the vector that it's giving us?
Yeah.
And this one, it's a plane, so the equation gets a little bigger because there's two vectors that define the plane, right?
Yeah. So the first thing is, I don't think web work is using a different convention than what we're using in class or in the book.
Yeah.
But when we have, here we go. I didn't even see that. If we're doing a projection onto a subspace. Now, in that example, that was the example that we had looked at in class, either yesterday or last class or class before last. We were looking at projecting it onto a line. So our subspace was a line that goes to the origin. In general, we can project it onto any subspace, so a line or a plane or a higher dimensional subset. This right here is the part not perpendicular to the line.
Which is from the line, right?
Yeah, in the subspace.
Oh, yeah, it's a scalar multiple, or the line is a scalar multiple of that, right?
The line is a scalar multiple of
that, the vector that it is.
Yeah, so long as this isn't 0.
Okay.
So if we, a very contrived example, we have a line here, and then we have a vector that's perpendicular to it, and we project this onto the line, then its projection will be the 0 vector. Because the orthogonal component of the part of this vector that's orthogonal to this line is the whole thing. All right, it's already orthogonal. So its projection will be 0. In which case, this line will not be a scalar multiple of the projection. Because the projection itself is 0. But in general, whenever there's a little piece of that projection, we can also think of that as a basis for the line. The line is itself all scalar multiples.
And then,
Of that. As long as it's not
yeah,
zero.
so that's the same thing also as saying the line is spanned by this vector. Right?
Exactly. If you pick one non-zero vector in that span.
Okay,
Because it's one-dimensional.
okay.
Right?
And so for more dimensions, it gets a little bit more complicated than that, right? When it's not just a line.
The computations become complicated.
Yeah.
When we do these, so we compute these things. Well, in general, there's a denominator. But these components, right, are these coordinates. We're computing one of these coordinates for each of the basis vectors.
And so in the one case, we're just looking at the first one because there's only one basis.
Because there's only
And
one
then
exactly.
Y hat gets, okay. That's why I was confused. I was confused there.
Yeah, so what you were saying was that it becomes more complicated. Computationally, it becomes more complicated.
Yeah.
But what we're actually doing,
It's still.
what we can say is true about it, is exactly the same in all of these situations.
Okay.
Yeah.
Okay, I just forgot about that particular equation. So when we were adding this stuff, I was thinking about that equation changing, but it's more that y is more complicated.
Yeah.
I'm not saying that right. But
No, I get you. This is, we have this general fact. No matter what what subspace we take in a vector space, then we can take that vector and find a part of that vector that's inside the subspace and a part of that vector that's perpendicular to subspace. It's exactly decomposed for those two pieces. So that's always true. In the simplest case that we can think of is one dimension. Well, simplest is zero dimension. But in one dimension, we have a line. We project our vector. Let's not make one that's orthogonal. Something like this. When we project it onto the line, we get this is the projection inside the line, and then this is the orthogonal piece of it.
Okay.
Right? This
So
thing
that's,
here.
the dotted part's the,
And the line intercept.
and then the other one is y hat, correct? On the x-axis?
Yeah, so the hypotenuse is y.
Okay,
The part along the axis that we want it to be in is y hat.
okay.
And then the part perpendicular is c.
All right, thank you.
Yep. So when we actually are trying to figure out what these things are and doing this kind of process like this, we have to do all these computations. Okay, we always have to do computations. But if we're talking about just, what can we do with these vectors, and we're not concerned with actually all the work of doing it, we're just saying what is true, what can we do? Well, we can always take, this subspace, and as long as we have an orthogonal basis for it, we can figure out what that thing is. Now, maybe we're not concerned with doing the work. We have a computer do it. Okay, we don't think about that. But we can always say that it's at least possible to do. If we had like a million dimensional subspace W, then we have a million different computations that we have to do with something on the scale of a million. And then it's a lot of work, right? But we do know that there is some projection in that space. No matter what the vector is, we can project into that, and then we can find what the orthogonal complement is. Okay, so, oh no, it's no problem. Like I said, this is what I want. So, we went through all the work of doing that in at least a simple, yes?
So, I guess we're about like looking at the grand process.
You're stepping all over my punchline.
Okay, sorry.
No, yes, that's true.
Okay. So like that process is practically like you go through the elements of your original basis and just taking one of those elements and subtracting like the projection of it onto the other basis element.
And you're left with, you're subtracting out the part that's inside the space, and you're left with the part that's perpendicular to the space. Yeah, that's exactly right. So that's where I was going with all of this. This was an example of something. That something is the Graham-Schmidt process. So this is an example of something right here. When we were doing this orthogonal decomposition, we needed an orthogonal basis in order to do this. If we wanted to find the projection, we had to have an orthogonal basis. What the Graham-Schmidt process does is it goes through this set of vectors that we're trying to figure out what these orthogonal pieces are, and says, well, the first one, let's just start writing out what it is. This is the Graham-Schmidt process, named after Graham and Schmidt. Google the first names because I don't know. Process only has one C. Why does that look so weird? Does it have two C's?
I think that'd be
Process? Process, okay. It just looks weird, that's all. That's all I'm saying. Okay, so if we have linearly independent vectors, x1 up to x k, let's say. We're not assuming that we have as many as so this is an Rn. We're not assuming that this is the basis for the whole space, but just some subspace. We just need that these are our, do we oh, see, they start off by saying it's a basis. Well, you know, we only need it for linearly independent.
Doesn't it need to be a basis to span the subspace?
In order to be a basis, it needs to span a subspace, the subspace that it's a basis of, right? But if we have linearly independent vectors, they're always a basis for something, the basis for the span of those vectors, right? So as long as they're linearly independent, they're the basis for something. Now, so what I've said is basically is exactly equivalent to what the book says. So if we have this, then we go through this step-by-step process, one step for each of these things. The first step is the easiest one. U1 equals x1. So we're trying to build an orthogonal set of vectors, an orthogonal basis for the same space. Oh, that's what I should have said. So this, in our first example, these two, there was some subspace that was spanned by these two things. Let's call it W. So it's the span of this and this. The span of this and this is the same subspace. So that's important. It's not just the same dimension. These actually span the exact same subspace. So our first step is exactly the same. Our second step is to take our second vector and subtract from it its projection into the subspace spanned by the ones before it. There's only one before it. This one is, we're subtracting away the span of we're subtracting away the component that's in the zero vector space, right? The component that's in the zero subspace is just zero. So we do the same. Zero. Nothing happens in that step. In this step, we're doing it with over the span of the things that are before it. And so in this case, it's x2 minus x2 hat, where the hat means the projection onto that line, onto this line. So that's x2 minus x2 dot u1 over u1 dot u1. In this case, u1 and x1 are exactly the same. In the direction u1. U3 is equal to x3 minus x3 hat, which is x3 dot u1 over u1 dot u1 in u1 direction, minus x3 dot u2 over u2 dot u2 times u2. This goes on. In general, as we're going through this process, we're going to say that ui is equal to xi minus the sum. Do you remember this notation from calculus before? J equals 1 up to I minus 1. So we're going to take this index j and we're going to go over all of the previous vectors. And the previous vectors, what are we going to do with them? xi dot uj over uj dot uj times uj. So it's that scalar multiple of uj. We're going to cut out all of the stuff that's in the subspace spanned by the ones before it. So finally we get down to uk is equal to xk minus xk dot u1 over u1 dot u1. I'll save myself some writing. I'm also writing this because in each case, we're really taking the vector and we're subtracting from it its projection. But each time, what we mean by that projection changes. It's the projection into the space spanned by everything before it. So the first one, everything before it is projection into the 0 subspace, which is nothing, so it's x1 minus nothing. Nothing happens there, and we get u1. In the second case, x2 minus is projection, but its projection is into the subspace of u1. Now u3, that one is the x3 minus its projection. So this is its projection into the subspace spanned by these two, and then we subtract out the part. Projection into these three, and then into these four, and we just continue this process. We continue this process. It's called the Gram-Schmidt process. We got 2 minutes left. What do I talk about enough time? I don't talk about anything.
Doesn't matter which order you love the x elements for the original basis or the set of the independent vectors.
Oh, absolutely not.
Okay, so it always just like scales up like orthogonal vectors that are like, let's say multiples, like regressive constructive.
If we start with these, this is I'm glad actually you said that, because I want to, well, for 2 reasons. The first thing is I want to make sure that I say that the span of these, so the subspace, this is a basis for the subspace. You get U1 up to UK. They span the exact same subspace, and they're also linearly independent. So they're also a basis for the same space. So this is a basis for W, this is also a basis for W, but this one is special, right? It's orthogonal, which means it's got all these nice properties about orthogonal things that we talked about before. Now, your question was, does the order in which we do these things matter? And the answer is yes and no. No, it doesn't matter because we will still span the same space. But yes, in the sense that we will end up with a different basis. It will be a different basis, but it will be a basis for the same space. So when we're handed the vectors, it's a set of vectors, and in many cases, we care about the order of those vectors because, you know, if we're writing down the coordinates with respect to the spaces, we have to write the coordinates down in a particular order. And that order depends on the order that we specify it in. But for the Gram-Schmidt process, it doesn't matter. We're just handed some vectors. We're handed a set, like a bag full of vectors. And we pull them out one by one. And in that process, we're giving them an order, right? We're saying this is the first one I pulled out of the bag. The second one I pull out is going to have something subtracted away from it, the part that's inside the first one. The third one I pull out is going to be the third one, and it's going to have to have something subtracted away, the part that's in the first two. That's the only sense in which the order matters, is that once you start the process, you have to know what things you're subtracting away from it.
Does it give us like like different information, or is it all
Depending on the order.
Yeah, like is it just like framing the same information from these points?
I have to think about that for a second. I don't think it gives us any additional information. Or it gives us the information. If we started with this one, we would get this as a basis, right? One way to think about this: if we start with x1, then our first basis vector is going to be x1, and it's going to be unchanged. It's going to be x1 and u1 are going to be the same. If we started with x2 instead of x1, and if we swap the order of these, then u1 is going to be x2 and it's going to be unchanged, but u2 is going to be x1 minus something, probably.
So if you have like an object moving three-dimensional space at a constant speed, you could define this movement, I guess this movement would be space based off like one of the vectors is going in. Does that make sense?
If we're talking about three-dimensional space, well, we want to say, if we're not talking about ahead of time, we specify what the coordinate directions are, x, y, and z, right? At some point in time, we just have three vectors that we know are linearly independent, and we want to specify the direction, the motion in terms of those. Then, well, we don't necessarily have to orthogonalize them, but we could do that, and in that case, we could do all these things. Okay, so, yeah. That's the Graham-Schmidt process. Was there, oh, it's 152, okay, I'm done. Yes.
So just because we extended on today, was the punchline of 6.3 that you can project on the spaces that aren't just lined? Because the chapter before we talked about orthogonal project, like I was saying.
Yeah,
But
exactly.
it was just lines. So the punchline of 6.3 is you can do it for things that are planes and many more dimensions.
The part of 6.2 that talked about the projection onto the line was a preview of 6.3. It was sort of like,
Special case, kind of.
it's exactly a special case.
Okay,
Yeah.
now we know the general form, project onto something, you expand out y hat, right?
Yeah, exactly.
Okay.
So as long as it's an orthogonal basis, we can expand out y hat easily. But if we don't have an orthogonal basis.
Then you just have the denominator, or not.
Well, I'm thinking if we have a basis, but it's not an orthogonal basis, how do we compute the projection into it? Can we do that? Well, using the Graham-Schmidt process, we can take that basis and create an orthogonal basis, and then use that as a projection. And as we said before, this projection isn't dependent upon the basis, even though the formula looks like, what do? We compute these things, we compute the coordinates, but the coordinates give us things that are pointing in the direction u1 and u2. And it seems like it depends on the basis whenever we do these computations. But as we showed the other day, it actually doesn't matter what basis we choose for the projection. But we need an orthogonal basis in order to do the computation of what the projection is.
Okay. All right, that makes sense. I just want to make sure I grasp.
Okay.
Correct.
And I can stick around for a while. I got multiple emails from you, but I haven't responded to any.
I think the first one, I got the iPad, and I did the 6.2 practice problems, and I tried to email it to you from the iPad thing.
Oh, yeah.
So it might have looked weird, but I figured I'd go, because I figured if I came in today with it handwritten, it wouldn't be back until Monday, and Monday we're reviewing, so I figured I'd try to shock them an email about the 6.2 one.
You make a good point.